Hi, this is Dr. Divya Bartaria, Head of Corporate Relations, United Group of Institutions, Allahabad. Welcome to this another session of phase rule. In this session, we will discuss the applications of Gibbs phase rule to a one component system. Before that, we will try to define the phase rule. Besides, in this first session, we will be applying phase rule on different systems in order to find out the values of phase, components and degrees of freedom. So, the agenda of today's lecture is Gibbs phase rule, application of Gibbs phase rule to a one component system, phase diagram of water system, and at the end I would try to summarize the things related to lecture 1 and lecture 2 both. So, let us come to the phase rule. What do we mean by phase rule? In earlier session also we have discussed that the phase rule is an important tool, a kind of versatile tool related to the study of behavior of heterogeneous systems. So, American physicist Willard Gibbs in 1874 deduced this general rule on the basis of thermodynamics, and it was H.W.B. Rosenbaum in 1884 who explained it further. So, according to the Gibbs phase rule, if a heterogeneous system is influenced by temperature, pressure and concentration and not by other actions like gravity, electrical and magnetic forces or by surface action, then the number of phases and degrees of freedom is greater than the number of components by 2. So, here you can see it is expressed mathematically as P plus F number of phases and degrees of freedom, its summation is greater than the number of components by 2. So, P plus F is equal to C plus 2. In that way, F is equal to C minus P plus 2. So, this is the phase rule equation, P plus F is equal to C plus 2, right. So, this is the definition and this is the phase rule equation. Now, if we are going to consider the application of Gibbs phase rule to a one component system, so we have to consider the number of component 1. So, for a one component system, how can we write down the phase rule equation? Let us see here. F is equals to C minus P plus 2. So, if we consider number of components as 1, so keeping 1 here, F is equals to 1 minus P plus 2. So, we get F is equal to 3 minus P. So, here you can see F is equal to 3 minus P. So, now this is the basic equation when we are going to consider the one component system. So, there may be 3 cases. First case, when only one phase is present. So, we are going to consider single phase system, P is equal to 1. So, in this particular case, if we use the same equation F is equals to 3 minus P, then you can see F is equals to 3 minus 1, that is 2. It becomes bivariant system. So, what do we mean here? That in one component system, when we are going to consider single phase system, there may be first case of single phase system, then degree of freedom comes out to be 3 minus 1, that is 2. So, what we can see that there are 2 degrees of freedom in one phase system. So, there is single phase equilibrium present in a one component system, and here 2 variable factors are required to define the system completely. And we will see it further that in a phase diagram of a one component system, there are certain areas which represent the single phase equilibrium. So, it would be a pressure temperature graph, it would be a phase diagram wherein there may be certain areas which would represent the single phase equilibrium. So, dear students, we have considered this first case wherein phase is equal to 1. So, here degrees of freedom is 2 and number of component we have already considered 1 here. Now, let us move ahead. If we consider second case and considering the base equation F is equals to 3 minus P, what we have discussed, F is equal to 3 minus P. Now, if we consider two phase system, or if we consider that there is a case when 2 phases are in equilibrium with one another, so F is equals to 3 minus 2, that is 1. So, the system becomes univariant. So, there are certain lines or curves present in the phase diagram of a one component system which represent 2 phase equilibria. So, whenever we will be drawing the diagram, phase diagram of a one component system, for example, water, So earlier we have considered that when there is a single phase equilibrium, it would be represented by areas. So here in the second case, we have seen that if the number of phases is 2, so if two phases are in equilibrium with one another, then there may be certain lines or curves which will represent this particular system, right. Phase is equals to 2 and the degree of freedom here will be 1, right. In detail we will be discussing it later. Now the third case, in the third case you can see when there are 3 phases. So if the number of phases is 3, then what will happen? F is equals to 3 minus 3, that is 0. So F is equals to 3 minus P, that is if the number of phases is 3, it becomes 0, it becomes an invariant system. No condition will be required, no variable factor will be required to be specified in order to define the system completely, and that is the triple point where all the 3 phases coexist, they are in equilibrium with one another. So you can see that this special condition can only be attained at a definite temperature and pressure. So a 3-phase system is represented by a point, triple point, in a pressure temperature graph, in a phase diagram of a one component system. So friends, we have considered the application of Gibbs phase rule to a one component system. So it is just a beginning wherein we have kept the basic equation, base equation as F is equals to 3 minus P, and have considered 3 equilibria. So let us see water system. We are going to consider water system. So water system is the most common example of a one component system, and water exists in 3 phases: solid ice, liquid water and gaseous water vapor. So all these are represented by one chemical entity, that is H2O. Therefore it becomes a one component system. So water is a one component system. C is equal to 1. Number of phases is, yes, 3. And now if we talk about different areas and curves, so we have to consider 3 equilibria present in the system. So there are 3 equilibria: single phase equilibria, 2 phase equilibria and 3 phase equilibria, as we have already discussed earlier. Now we can see that in this diagram represents the phase diagram of a water system. This is a pressure temperature diagram. Along the x axis you can see that this is the temperature and this is the pressure. So you can find out that there are certain areas, these are the areas, right. So this is ice, this area represents ice, this area represents water, and this area represents water vapor. This is water vapor. So this is the phase diagram of water system, wherein you can see that 3 phases are present here. And in this particular phase diagram, we can find out 3 areas. There are 3 areas: BOC, right, BOC, then AOC and finally AOB. So these are the 3 areas. Then there are 3 stable curves: OC, OB and OA. So these are 3 stable curves. There is one triple point, this is the triple point, right, and there is one metastable curve as well. Where is this metastable curve? This is shown by a dotted line, OA dash. This is the metastable curve, right. So in a broader way you can see, you can have a glimpse of this phase diagram. You can find out that there are 3 areas, 3 stable curves, 1 metastable curve and 1 triple point. We will try to give a kind of explanation of each and every area and the curves along with that triple point. So let us come to the first curve, which is OA. Now as you can see that it represents the equilibrium between water and water vapor, right. This is the curve OA. It represents the equilibrium between water and water vapor. This is water and this is water vapor, and that is why it is known as vaporization curve, right. So what you can see that water is in equilibrium with water vapor. Along this curve 2 phases coexist in equilibrium. What are these 2 phases? Water and water vapor. And this curve shows vapor pressure of liquid water at different temperatures. Now in the diagram you can very easily see that this curve terminates at the critical point A. This is the critical point. This is the critical point. Now what is this critical point? This critical point corresponds to the temperature. You can see it is 374 degrees centigrade and the corresponding pressure is 2.18 atmosphere. So, at this critical point, this is the highest point, highest temperature at which liquid can exist. So, at this critical point, water and vapor become indistinguishable to each other, and thus only one phase is left after this critical point. So, this is the critical point which marks the highest temperature at which the liquid can exist, and before that there is an equilibrium between liquid water and water vapor. Also, you can see that this is the temperature 100 degrees centigrade and this is the pressure 1 atmosphere. So, at 1 atmospheric pressure, the corresponding temperature is the boiling point of water, which is 100 degree centigrade. So, along this curve you can finally say that the number of phases is 2. So, this curve represents 2 phases in equilibrium, number of phases is 2, number of components is 1 only, and if we talk about the degree of freedom, then you can use that formula also, F is equal to C minus P plus 2. So, by putting all these values you will find that the degree of freedom will be 1 only. And also here you can very easily find out that if you fix the temperature, then the pressure and composition will get automatically fixed. Similarly, if you fix the pressure, then the temperature and the composition get automatically fixed, and this is all about degrees of freedom. So, all the lines and curves represent the univariant system, that is degree of freedom will be 1 only. Now, let us move ahead, and this is the curve OB that we are going to consider here. What is curve OB? This curve OB represents the equilibrium between solid ice and water vapor. So, solid ice and water vapor means it represents the process of sublimation, and that is why it is also known as sublimation curve. So, curve OB represents the equilibrium between solid ice and water vapor, and it is also known as sublimation curve of ice. Along this curve, 2 phases coexist in equilibrium. It shows the vapor pressure of solid ice at different temperatures. You can see here. At the lower limit, curve OB terminates at absolute minus 273 degrees centigrade, where no vapor exists at the lower limit, right. So, along this curve you can see that number of phases is always 2 and number of components is 1, and as we have clearly understood that along any curve or line the degrees of freedom will be 1 only. So, here degree of freedom is 1. Let us come to the curve OC. This is the third stable curve that we are going to discuss. Curve OC. This curve represents the equilibrium between solid ice and liquid water, and that is why it is also known as melting or fusion curve. Now, you can see that the very little inclination, the very little slope of this curve as well as its inclination towards pressure axis is just because of the abnormal behavior of water and ice. All of us know that density of ice is less than that of water, and because of this, the slope is very low and it is inclined towards the pressure axis. Now, the curve starts from point O, it starts from here, and beyond that there is no limit for this curve. It goes up to a point corresponding to 2000 atmosphere pressure and minus 20 degrees centigrade. So, along this curve again you can see, you can very well explain that number of phases is 2, number of components 1 only, and degree of freedom will be 1. So, in this way we have defined all 3 stable curves, right. So, all 3 stable curves or all 3 lines or curves represent 2 phase equilibria. Now, if you come to the triple point, at triple point you can see that all the 3 curves OC, OA and OB meet together. So, this curve or this point represents a point where 3 phases are in equilibrium with one another, all the 3 phases coexist. So, the equilibrium in these free phases is attained at 0.0075 degree centigrade temperature and 4.58 millimeter mercury pressure. So, at this point you can see that phase is equals to 3, number of components is equal to 1. If you use that formula, then also you will get F is equals to 0, and also you can see that no condition has to be specified here. So, degree of freedom will be 0. So, it is very important to understand the significance of this triple point, because if any of the 3 variables, either the pressure or the temperature or both, are changed, then the 3 phases would no longer coexist, and at least one of them would disappear. And this is the significance of the triple point. There was another curve, metastable curve, that you have found here in this diagram. So OA dash, I am talking about curve OA dash, right? So the students get confused that it shows the equilibrium between solid ice and water vapor, right? It seems as if it is representing the equilibrium between solid ice and water vapor, but it is not so. Why? Because it is actually the extension of the curve OA, right? So this dotted line, this metastable curve, is the extension of this curve OA. So it represents the equilibrium between liquid water and water vapor. But this is the supercooled water, right? So this at the first point you can see that curve OA dash is a metastable curve shown in continuation of AO and shows the vapor pressure of supercooled water. This is the vapor pressure of supercooled water, right? So what do we mean by supercooled water? So you must remember that with due care, it is possible to cool water below its freezing point without the separation of ice. Then the water is said to be supercooled, right? So the liquid water system along this curve OA dash is said to be in metastable equilibrium, as even the slight disturbance in this phase changes the supercooled water into ice, and then the curve OA dash merges into OB, right? So if we create a little disturbance, then this curve will merge into OB, and in that way solid ice will be separated out, right? So this is how we can give a kind of explanation for this metastable curve. This is also known as metastable curve, as you can see that this line, this curve lies above OB. Its position is always above OB, this stable curve, and it has higher vapor pressure than the stable one at the same temperature. And that is why it is also known as metastable curve, right? Now let us consider a few questions. We will consider two questions here. First question is it possible to have a quadruple point in the phase diagram of a one component system, right? So give a thought in your mind. Is it possible to have a quadruple point in a one component system? So in a one component system means C is equals to 1. So you have to fix C is equals to 1, and then you can find it out that no, it is not at all possible to have a quadruple point in the phase diagram of one component system. Why? Because quadruple point means P is equals to 4. There are 4 phases in equilibrium. One component system, you have already noted, C is equals to 1. So if we use this formula, F is equals to C minus P plus 2, then you will get a negative value. So negative value of degree of freedom is not possible. So with the help of this equation, with the help of this concept, you can clearly mention that it is not possible to have a quadruple point in the phase diagram of a one component system. Now the second question is determine the maximum number of phases in a 1, 2 and 3 component systems, right? So in order to have maximum number of phases, degree of freedom should be 0. In this formula you can very easily see, you can easily express that in order to have P maximum, phase maximum, F should be 0. So for one component system, it should be 1 plus 2, that is 3. For a 2 component system, P maximum should be 2 plus 2, that is 4, and for a 3 component system, it should be 3 plus 2, that is 5. So the answer is, for a 1 component system, maximum number of phases would be 3. For a 2 component system, maximum number of phases would be 4, and likewise for a 3 component system, number of phases would be 5. I am talking about number of maximum phases. So friends, this is all about phase rule. I hope you liked this session, and if we consider both the sessions, session 1 and session 2, you can have a clear idea of the phase rule, its application to one component system, and further in future on the basis of your queries and doubts we can have another sessions. Thank you. You can catch me at 9628829329. Thank you very much.